Hello all. Today I will be presenting the simulation of oscillating lid-driven cavity using unsteady Navier-Stokes equation. The objective of today's presentation is to modify the previously solved lid-driven cavity problem with top lid moving in one direction at constant velocity. In this problem, the top lid oscillates, giving us a harmonic function. This problem is solved with artificial compressibility method on the unsteady Navier-Stokes equations. We want to visualize how the velocity contours change as the top lid moves to and fro. Apart from this, we would also be comparing results to benchmark solutions. So, lid-driven cavity. This is often referred to as a benchmark for testing several numerical methods. Lid-driven cavity, as the name suggests, moves the fluid within due to the moving top lid, as you can see here, resulting in the formation of streamlines, as shown in these images. You can see the streamlines being formed here. We have previously worked with steady-state governing equations, which are given as follows. This is the continuity equation, and this is the Navier-Stokes equation. With steady-state equations, an artificial equation of state is introduced while solving the problem with artificial compressibility method, as it is given over here. Beta represents the artificial compressibility factor. With this artificial equation of state, the continuity equation is modified to include the artificial compressibility factor. And as the time-dependent term goes to zero at steady state, we get divergence free flow. Using artificial compressibility method to solve the unsteady Navier-Stokes equations is not much different. We need to take into consideration a second time step, pseudo time step in the governing equations. The reason for this is that there are several pseudo time steps between two physical time steps. So instead of jumping from one physical time step to another, we advance over multiple pseudo time steps. This ensures local convergence. This ensures that local convergence is achieved before advancing to the next physical time step. Thus, the continuity equation remains the same, only with the pseudo time step instead of physical time step. As you can see here, it is given by tau. And in the Navier-Stokes equations, we have an additional time-dependent term where the time is taken as the pseudo time step, this term over here. So, coming to the most essential part of lid-driven cavity problem, the boundary conditions. A staggered grid was used for the simulations, which is shown in this image. The u velocities occupy the vertical centers of the face, as indicated by the blue arrows. The v velocities occupy the horizontal centers of the faces, which is indicated by the brown arrows, and the pressure points occupy the face centers, the black points. The most important boundary condition is the top boundary condition, which in a standard lid-driven cavity problem moves at a constant velocity in horizontal direction. This as indicated by this image. And the bottom wall is stationary, and the left and right walls have no slip boundary conditions. In the current problem which is presented, the only difference is in the top boundary, which oscillates at a constant velocity given by this formula u equals cos 2 pi t. Next, I'll go through the results. These plots here show the variation of the velocity as the lid oscillates. It can be seen in the first two images that as the lid moves forward, the velocity becomes maximum. The next two images show that the velocity goes down to almost zero as the lid moves back to the original position. And the next few images show a blue velocity contour, which means that the velocity is going negative as the lid moves backwards and coming back to zero as the lid comes back to the original position. Next, are the steady state streamline plots. This plot is for the lid-driven cavity with the top lid moving in the horizontal direction at a constant velocity, and this plot is for the current lid-driven cavity problem. It can be seen that the primary vortex has shifted a little towards the top, and the secondary and tertiary vortices have become like very, very small. Next, and lastly, we check the u and v velocities along the vertical and horizontal center lines respectively. Here I have tried to compare the results with the solutions of GIA, and we can see that the solution differs considerably while comparing the two lid-driven cavity flows. However, the results still seem to match the plots given in the bottom image, like these plots for Reynolds number equal to 100. Lastly, we go to the conclusion. The results for variation of velocity contours as the lid moves to and fro was validated by the simulations. The steady state streamline showed some difference as the primary vortex moved towards the top and the secondary and tertiary vortices were very small. And the U and V velocities along the center lines did not really match the benchmark solutions given by GIA. Thank you. And if you all have any questions, please feel free to ask. Thank you.